All right, so welcome everybody to Hoon School Live Lesson 3. So in last class, we learned about how to use Hoon's type system for atoms, right? For single values. So we learned that atoms can be cast to each other if they nest in a tree-like structure like this, right? And we used the Kethep rune, this rune, as a fence to make sure that the result of a computation can pass a certain type. For example, we can have a statement like this saying, let me call add on 1 and 2 and make sure that passes as a pat UD, and it does. And we also learn how to use the Ketless rune, this rune, to do the same thing, but with an inferred type. So we can say, let me add 1 and 2, and let's see if it passes as the inferred type of Zod, which is a pat P, right? So we run that and we get West, which is 3, the number 3 converted to a pat P. And we also learn how to get the default value for an aura with this rune, tar. So to get the default value of a floating point, just 0. And we also learn how to use the sugar for it, right? Just like that. So this is all great, but so far we're just dealing with single values, right? For general computing, you need types for more complicated structures like cells, tuples, lists, set maps, and all sorts of different structures, right? Hoon covers these sorts of types with what's called a mold. So to use a chemical analogy, if atoms are like atoms, like hydrogen, oxygen, molds are like molecules, more complex structures that are built bit by bit out of atoms. And molecules can be simple like water or complex like DNA, and that same thing goes for molds. All right, so when you're writing Hoon to specify a mold, you're in what's called structure mode. And structure mode is when the Hoon parser is interpreting your code as a specification for a type rather than directly writing something that computes a value. So let's look at an example to understand this more clearly. So if we just look at this line of code here, it's pretty straightforward, right? So we have this tisfaz rune. We're saying pin this face word to this value hello, and then just return the word. So if we press enter, it returns hello, right? And we could have also added a bit of type information to this face word as well. So this is saying, let me pin the face word to the value hello, but also the face word must have aura pat T. All right, and running that does the same thing. So it turns out this is actually sugar syntax for the following rune. This rune right here, it's called Buktiz. So Buktiz, what it does is it takes 2 children. The first child is a face, and the second child is a type. And it just says that face has to refer to something of that type. We're constraining what this face can represent. So here we're constraining word to be a type of pat T. Importantly now, we've seen 2 different kinds of syntax where you write like A equals B now, right? So in particular, we've seen directly assigning a word to a value or a face to a value like this, word equals hello, right? Or you could even do this in a more complicated way, like A is a cell of word equals hello and num equals 2, right? Or you can use that syntax, how we just used it, to specify that word is a certain type, right? And now it's important to know that these 2 syntaxes, even though they look very similar, they actually refer to different usages. And they depend on whether you're in value mode, talking directly about values, or talking about structures. So in last class, you may recall that we learned the Ket-Tis rune, right? And that rune is value mode, assigning faces to values. So that's what we used above when we did like word equals hello. So if you recall, we had examples like this, right? We're setting this cell of faces, BCD equals XY, to this cell of values. And it had a sugar syntax like this, right? It looked like this. You could just set BCD equals XY equals to 1, 2, 3, 4, and it's a sugar for this rune, right? However, the Ket-Tis rune is in structure mode, so we're setting a face equal to structure, so that's a little different. In particular, if you look at these examples here, when we set word directly equals to hello, that desugars to Ket-Tis, and when we set word equals to a type, that desugars to Ket-Tis. Are there any questions on that? All right, so if there's no questions, I'll be moving on. So let's go through an example of actually building and using a simple mold using structure mode. Suppose that we wanted to make a bank app, right? So we might represent people's accounts by their PAP-P. And for each account, we might want to store how much money they have, maybe in a floating point number, right? And we want these two values to be linked together, like this amount of money goes to this person's bank account. So to do this, we're going to use a new rune called Buckcoal. Buckcoal takes an indefinite number of children. So we saw this before, right? When the rune doesn't know how many children it's going to take, we close it with this tis at the end, so the parser knows when you get to the end. And basically, each child is a specification of a type. So if it has 2 children, it creates a type that is a cell of 2 things. If it has 3 children, it creates a type which is a triple of 3 things, and so on and so forth. So let's go through an example of how to use it. So look at this code here. This code is saying, let's pin to the dojo under this face called bank account, Buckcoal to make a type. This first child here is Ket-Tis, which is setting this face ship to this type PAP-P. And the second child of this Buckcoal is this, which is setting face money to PAP-RS. And finally, we're closing off the Buckcoal with a tis. We press enter. Okay, nothing happened, but we want to make sure that we did this right, that this new type now works. So what are we going to do? Certainly, if we have a cell that looks like this, right? Yeah, first entry is Zod, and the second entry is dot 1, 2, 3, 4, 5, 6, dot 7, 8. So this certainly looks like a PAP-B. This looks like a floating point, right? So let's check it. We can use this bank account mold just the same way that we used auras. So we can use it with kethep, and we can kethep this cell with our bank account mold. And it returns a cell with the faces, ship and money attached to the values. So that's pretty nice, right? And you can also use a sugar syntax. So you can just do tick bank account, tick the cell, and does the same thing. And for clarity, we could have, instead of using this face, we could just write the whole thing out. So what we have here is, instead of like the word bank account, we just substituted like the actual definition of bank account right here, right? So here's, if we have this long expression, here's how we like parse it. Here's the mold, here's the value. Those are 2 children to this cat. All right. So what exactly is happening when we do this type checking? So what happens is the parser says, okay, in my mold, the first thing is a pat P, then it looks at the value, looks at the Zod, and it says, I infer that this is a pat P. Pat P nests under pat P, so you're good to go there. It looks at the second thing in the mold, and then the second thing in the value, and it infers that this is a pat RS, and then it checks that pat RS nests into pat RS, and then it says you're good to go. And having passed all the checks, then it returns this with a face attached. So what happens if we try to mess this up? So we could put the text hello here. And what's going to happen if I press enter? We have this error called nest fail. You needed a pat P, but you have a pat T. It's hello. So it's checking this, inferring a pat T. Pat T doesn't nest into pat P, and you get the nest fail. And if you do the following, just like 1 and 2, that shouldn't work either, right? Because well, what's going to happen is it infers this as a pat UD. Pat UD doesn't nest into pat P. Pat UD doesn't nest into pat RS, and you get a nest fail. So are there any questions on that so far?
So does the bug call rune create structs in another programming languages? Is it something like that?
Yeah, it creates types. I'm not too familiar with, like, I guess there's a reference like C, right? So I'm not too familiar with that language, but I suppose so, if that's the equivalent of like types.
Yeah, okay, thank you. Yeah, Ian, by the way, I was talking about C structs also.
Cool. Yeah. Can the values be inverted? Nope. So yeah, that's a good point. So let's try that. Cat hat bank account. Let's invert the values and see what happens. And it's going to say, I expected a pat P in the first position, and then there's a pat RS after the. Well, I mean, this is the same thing. This what we did here is the same thing as this, or sorry, as well, I have the hello, but so this is the same thing as this. We just substituted the word bank account for this expression. So if I reverse these, it also won't work. It's the same thing. So it's checking every position. So the positions matter.
Is it only checking the first instance? Like
well,
it says it needs a pat P. Yeah.
And so it checks the first instance, and that already gives a failure, so that it just fails based off of that. If that one passed, then it would check the second one. So I could give Zod, like if I did a Zod, then the first one passes, but the second one fails because, right, the second one is passing. Need pat RS, have pat P. And sorry.
No, okay, yeah, thanks.
Okay, cool. And so I'm writing this entirely in tall form. Usually you'd see this in a sugar syntax. So the first sugar syntax you'd probably do is sugar this but tis. So then you'd write it just like this. And that's the same thing, right? So this is just corresponding to this is corresponding to this. And you can even sugar away the bug call on the outside and just write this as a cell. That's very nicely readable, right? But it's always important to understand what the sugar syntax is underneath. So in this case, this cell is actually this bug call. So that does the same thing. And there's also an important and subtle point here in that suppose like I want to use TISFAS to create my new mold. I can also sugar that as well, but usually like when you use TISFAS and you have a face, and it usually expects a value here. right? It doesn't expect like a structure or type. It expects like a value, like you would do like his FAS numbers is the cell of 1, 2, like the actual value is 1, 2, and then return numbers, return the numbers, right? And in this cell, like in this case, this desugars to this Cohort that we learned before, right? So if you want to write like bank account using this syntax, you have to use a different syntax, which is like looks like this. Yeah. So this basically looks like what we did, except this COM here is distinguishing. This is saying we are in structure mode. This is a structure mode expression. This is not a value mode expression. So yeah, that's because this TISFAS expects a value mode here. So you have to tell it it's in structure mode. Whereas when you're using Cohort, it's expecting a structure mode here already. So you don't need to specify that. Are there any questions on that? That's a little subtle point, but yeah. All right, if there's no questions, I will move on. So let me show you something interesting now. So what if I do this? What if I do this? There's a different room here. This is not Cohort, this is SENHEP. What if I do this and press enter? Oop. Oop. So it returns something. It let me type that and press enter and return something. And if I just do the same thing with the Cohort, right? So recall. Oops. That was a nest fail, right? So what are we doing with this rune? What does this imply? We remember what this rune does, right? So what are we doing here? Here. Anyone remember what SENHEP does? Yep. Calling a gate. So it turns out that molds are actually gates. You can use them as gates. And this gives different behavior than casting it with a Cohort. So when we use Cohort, we're doing the element-wise checking on each entry in the value, right? And making sure each position matches the type that you specified. So that's a very safe thing to do, right? When we call it as a gate with SENHEP, we're actually treating this noun just as a raw noun. So we're saying strip all the type information out of this. So just reduce this to the underlying like positive integer. Take those positive integers and then make them fit this mold. So that's why when we did this, we actually got a ship. We turned this hello text into a ship, which is Das Pel Begrig Famto. So that's kind of interesting, right? And you can do this with like you can just do it with the numbers 1 and 2, right? And you can turn those into ship and pat RS floating point. And you could use the floating the sugar expression for this as well. So that's the sugar for calling gate. So these two usages of molds are really two different things. So we have casting, checks element wise, crashes with nest fail if it doesn't fit. And importantly, casting is done at is checked at compile time, which means it's only checked once when you build the code, and it's going to give you an error when you build the code. So it's not going to pass an error onto the runtime if you're doing this. This is safe, right? This molding with the gate coerces the result to the mold, drops all type information, uses the raw now, and it happens at runtime. So it happens every time that the code is run, which means that this could throw a runtime error when like your user is using an app or something. However, molding is still very useful. You just have to be safe when you do it. And what people do is they use casting and molding together. That's quite common. So I'll give you an example of how molding can fail. So we know that bank account is a cell of 2 things, right? So what happens if we pass it a cell of 3 things? We'll get a Dojo Hoon expression failed. So yeah. Any questions on that, on molding? What happens to extra information? So the original type information from the result of this argument gets thrown away. The question was, what happens to extra information when molding? If that's what you meant by extra information. All right, any other questions? Like if the tree of the noun or molding has more branches. Right, so that's exactly what happened here, right? So bank account was expecting a cell of 2 things, whereas this 1, 2, 3 is actually a cell of 1 and 2, 3 underneath, right? So there's more branches here than like if it was just cell of 1 and 2. And that caused a crash because the shape didn't fit. Yeah. Yep. All right. So if there's no more questions on that, gonna be moving on. So there's one more rune we should learn for making molds. Suppose for whatever reason you wanted to create a type that's either a text or a floating point number or a date. So it's one thing, but it can be like several different types. This is what's called a type union. And you create it with the following rune, which is called buck what. So it takes an indefinite number of children and it creates a type, which is the union of all these types. So let's try this here. I should be giving you guys all these code. I forgot to do that, but here you can try this if you'd like. So here we're going to make a new type, which is buck what, a pat T or a pat RS or a pat DA. And now if we try to type check like a date, like today, then it'll pass. And if we try to type check a number, a pat UD, we'll have a nest fail because we have a pat UD, but it expected either a pat DA, a pat RS, or a pat T. Something kind of unique is this will accept pat T, but what it does is it actually casts it to the last type in the type union. So it accepts this pat T, but it casts it to a pat DA, and it'll accept a pat RS. It'll cast it to a date. So yeah. This type union is not usually used with like the raw types like this. If you'll recall from last lecture, we learned about terms, right? Which are like sen something. And those are all their own unique type, right? So they're both like a text constant and they're also unique type. So this type union is usually used with those types. Right, so it accepted the string and float because we made a new type. We said we have a type union, which is a union a bunch of different types, right? So we're unioning text, float, and date. So we're unioning those 3 types, and this type should accept all 3 of them. It's just the quirk that it casts them all to the last one, but it accepts all of them. And it didn't accept the pat union. Does that make sense? Okay. So like the application you'd usually use this rune in is like in the following. So I'm making a new type called reptile, which is a union of either sand snake, sand lizard, or sand crocodile. We need an extra space there. And now, having pinned this definition to my dojo, I can do cat pet reptile sand snake, and I'll return sand snake and let that pass. Do elephant. They'll say have send elephant, need send crocodile, send lizard, send snake. And the sugar syntax is like this. So it's just this what in front, and then parentheses, and then the arguments. Just too many spaces there. Yeah, like that. That's the sugar syntax. And then you can do the same thing. And you can even call it as a gate. So if I call reptile as a gate on this number, that's actually the underlying integer for sand lizard. So I did that in advance, and it allowed me to call it on that. If I just used a random number like that, you get a failure because that number doesn't parse to any one of these. All right, any questions on type unions? All right, so if there's no questions, I'll be moving on. Suppose that you are running a reptile care facility and you need to create a data structure to keep track of it. So let's say you need to keep track of your reptile and how many meals it's had this week, right? So we already created this reptile structure, right? And then we can even use that. So we can combine these rooms. We can combine making a cell type with making a type union like this. So I'm creating a new type called reptile tracker. I'm using a buckhole, just creating a cell type, just saying the first thing has to be one of these and the second thing has to be one of these. And we're saying the first thing is a species equals type reptile. And the second thing is meals, which is a type PAT-UD. And we can use that to fence a value. So certainly send crocodile 3 should fit this mold, right? And it does. It returns us with faces attached. And we can also call that as a gate, like so. So any questions on that? Yes, 4 meals a week. Not bad for a reptile, I think. All right, so the next topic is bunting. So just like with atoms, we can get bunts or default values for all the molds we just created. And we just use the same rune as before. So if you recall, we made the bank account rune, bank account type, mold, sorry. And we can just do ketar bank account. And what that does, this is a cell type, right? So it just goes to the first thing in the cell and says, that was PAT-P. Let me get the bunt of that, which is Zod. And the second thing was PAT-RS. That's a floating point. Let me get the bunt of that. That's 0. And then it returns the bunt of those 2 bunts in a cell. And so ketar just operates kind of recursively on cells like that. And we could have done this with sugar syntax as well. If you have a type union, it defaults to the last thing in the type union. So if you'll recall, new type was a type union of PAT-T, PAT-RS, and PAT-DA. So if we bunt new type, you actually just get a bunt of PAT-DA. If you bunt reptile, you just get send crocodile because that was the last one. And you can bunt reptile tracker, which just bunts the first thing, which was reptile, and the second thing, which is pat UD. So yeah. Any questions on that? That's the end of the mold section. So if you have any general questions on molds, definitely feel free to let me know right now. All right, so the next major section of our lesson is going to be about making decisions. So in computer programming, making decisions based on whether a condition is met is really fundamental and important, right? So if this, then do that, otherwise do that, right? Hoon has a family of runes for doing this. It's called the what family of runes. They're pretty straightforward to use and understand. So the first rune that we're going to learn, and probably the most fundamental one, is the what call rune. So it takes 3 children. The first one is a Hoon expression that reduces to either send.y or send.n. The second child is an expression to evaluate if this is send.y. And the third child is an expression to evaluate if this is send.n. So pretty straightforward, right? And the simplest possible way we could use this is just like this. So we have what call. First child is send.y. Second child is 1, and third child is 2. So this should return a 1, right? Because we're going down this branch. This is a yes. So press enter, and we get a 1. And if we just change this to send.n, it'll go down the other branch, and I'll just return a 2. And that's pretty straightforward, right? To learn some usages that are a bit more complex, let's take a brief detour and learn some arithmetic comparison operators in Hoon. So basically, there's standard library gates. So we learn like add, div, mul, and so on, right? You can also just compare the sizes of different atoms, and they're pretty straightforward. So if you call GTH on 1, 2, you're asking, is 1 greater than 2? And the answer is no, right? And GTH is 2 greater than 1? Yes, 2 is greater than 1, right? Is 10 greater than 10? No, because something isn't greater than itself, it's equal to, right? So you get a no. Is 1 less than or equal to 2? Yes, 1 is less than or equal to 2. Is 2 less than or equal to 1? Nope. And is 10 less than or equal to 10? Yes, it is. So any questions on these? All right, so going back to our what runes, since we have these and they return send.y or send.n, we can then just plug in expressions using these into our what call rune. So let's try this. First, let's set x equal to 3. Then let's have this expression. So what's going on here? All right, so this is our full expression. I'm not going to press enter yet, but we're setting x equal to 3. We have a what call, and then its first child is something that results in a Boolean, right? So we're saying greater than x2. Is x greater than 2? What is x? X is 3. So 3 is greater than 2. That means this evaluates to send.y, which means we should take this first branch, which prints out the statement it was greater than 2, and not the second branch, right? So if we press enter, then it does exactly what we expected. It prints out the statement it was greater than 2. If we do the exact same thing, except set x equal to 2, so this is the exact same code. All we changed was set x equal to 2. 2 is not greater than 2. So we should take the second branch, right? And indeed, it prints out it was not greater than 2. We can set x equal to 1. It's the same thing. It was not greater than 2. And you'll most commonly see this in the sugar syntax. So the sugar syntax looks like this. So that's just the sugar syntax. And like you can, instead of directly returning like some literal, like just a text string, you can also do like more complicated stuff. So you can say set x equal to 1 in if x is greater than 2, we return the result of adding 1 to 30, or sorry, x to 30. And if not, then we return the result of adding x to 20. So we compute that and we get 21 because we took this branch and we returned add 120. And if we change this to 5, then we take this branch and return 35. Any questions on that? Cool. So Hoon has the equivalent of not and an or, like these basic logic operations that you'd expect to see in any other programming language. So the rune for not is WhatsApp, and it's pretty straightforward. Just takes one argument, which is a Boolean, and just reverse it. So we pass in a send.y and we get a send.n. Pass in a send.n and we get a send.y. And if we pass in something that reduces, so is 2 greater than 3? No, it's not. So this would be a send.n. We reverse that with this room, right? So we should get a send.y and we get a send.y, right? And there's also a sugar syntax for this room, which is just the zap and then the rest of the expression. So this is saying, is 2 greater than 3? No. Reverse the result of that. So reverse that no to a yes. That's what this is doing. And we get a yes. So the rune for logical and is what Pam, and it works like this. So it takes a indefinite number of children, so we have to close it with this tis. And if you'll recall what logical and is, it says if all of these conditions are true, if all of them are true, then the whole thing is true, right? So here we have 3 yeses but 1 no. So because of that 1 no, the expression should return no. And if we change this no to a yes, the expression will return yes. And the sugar syntax for this just looks like this. So you just have this Pam in front and this parentheses, and then all your arguments here. And you just send out y. Sorry, that's all. What does that mean? So you can have more complicated logical expressions if you'd like, right? So you don't have to directly have this literal here. Like an expression like this is saying, let's compute the and over is 2 greater than 1, yes. Is 3 greater than 2, yes. Is 4 greater than 3, yes. But we're reversing it with this that, right? So that's going to be a no. So this is going out to yes, yes, no. And so that means this whole and is going to evaluate to no. And if we just remove this, we get a yes, right? And we could have wrote this whole thing in sugar syntax, just like this. So there's a rune for logical or as well. So it's pretty much the same structure-wise as the logical and. And if you recall how logical or works, if all of these are no, then the result is no. If just one of them is a yes, then the result is yes. The sugar syntax looks like this. So it's just a bar and then the parentheses and then your arguments. And we could have done the same more complex things with it too, right? So we're saying 1 is greater than 2, no, it's not. 2 is greater than 3, no, it's not. 4 is greater than 3, yes, it is. So this is no, no, yes. And that one yes should make this whole thing yes, right? Here's the sugar syntax version. I should have been typing these in the chat. It's my bad. Here, I'll throw these ones out for you. All right, so any questions on all those logical runes that we just learned? All right, so if there's no questions, I'll keep moving on. So there's also something more interesting we can do with these branching decisions. We can also make decisions based on something the type system knows. So let's learn this rune. It's called what sig. It takes 3 children, so kind of like the what code, right? And this is an expression that it'll evaluate to something. If that something evaluates down to just sig, like the null character, then it'll take child 2, otherwise it'll take child 3, right? So what happens if we do this? Let A be sig in if what null A, and if it was null, then we print it was null, and otherwise we print it was not null. But actually, if I press enter here, it has an error. It says mint vain, Dojo expression failed. So this is kind of a cryptic error, and it's one you might come across quite often when you're coding in Hoon. So it's important to know what this is and what it means. So what happened here is this character sig by itself is its own special type. So the Hoon compiler knows exactly what A has to be based on this type information. It knows A can only be this. Because it knows that, it's saying, okay, I have a what sig here that's doing branches based on whether A is sig or not. And I know A is sig, so I'm always going to be taking this branch. And the Hoon compiler knows it's never going to take this branch. And the mint vain error means that you have a branching expression and the compiler knows that you cannot take one of the branches. The one of the branches will never be used. So what can we do? We can confuse the compiler by casting the sig to PAT-UD. And then, yeah, dead code detection, dead branch detection. It's a good. So if we cast a sig to a PAT-UD, we do the same thing, then the code runs. Because a PAT-UD, like, it can be 0, it can be 1, it can be 10, it can be 100, right? The compiler doesn't know what exactly something of a pat UD is going to be. And like casting sig to a pat UD just results in the number 0. So this is actually just the number 0. And because the number 0 appears to the compiler as a pat UD, it doesn't know that's just going to be a sig. So it lets you run this code. So I could have done this same code with the number 0, and it'll work. And if I do the number 1, you get it was not null. All right, yeah. So are there any questions on that? This is kind of a tricky error that people will find. So. All right, so that's pretty basic, right? But there's more powerful stuff that we can do by using types as a conditional to branch on. Recall that earlier we made type unions, right? And in particular, we made a type union of like a reptile like this, right? So we're saying a type reptile is either a sand snake, sand lizard, or sand crocodile. I need a space. And we can use these in a very powerful way with switch statements. So what are switch statements? We're going to learn this rune called whathep. So the first child to whathep is the input argument. The second child says, if this input argument matches this type, then do this thing. And if it matches this type, then do this thing, and so on and so forth. You can have as many pairs of these as you want, or as you can't have more pairs than there are types of the input of the type union. But yeah, and then you close it with this tistis. So I'll show you what I mean with an example right now. So if we have this reptile pinned to our dojo, we can do this following code. So we're saying let R be sand lizard, which we cast to make sure it's of type reptile. And then we have a switch statement like this. So if I run this code, it's saying, let's switch on R. If R is sand snake, print I'm a snake. If it's sand lizard, print I'm a lizard. And if it's sand crocodile, print I'm a crocodile. Tis closes this expression. If you press enter, you get I'm a lizard. And you could just change what R is. You could change it to snake instead, right? And you get I'm a snake from the switch statement. If the switch statement has an extra branch, so if it has a branch that the compiler knows that you'll never be able to take. So reptile was a type union of sand snake, sand lizard, and sand crocodile. It had no sand alligator, right? So if you add this branch, you get the mint vein error, which you saw earlier, right? So this is saying we have a branch that we're going to take, and the compiler knows that. So any questions on using this whathep rune?
So what if you have only snake and lizard?
Yeah, let's try that. I think it'll work. So actually that throws another type error. And this type error is saying that there is a case for this type that we're not covering. So good question. But the next rune that we're going to learn, it actually teaches us how to deal with this. Before I go there, are there any other questions on whathep? All right, so the next rune we're going to learn is called whatplus. So it's just like what hep, except it defines something to do if you don't get a match down here. Yeah, it'll fail if you miss case and match statement, but that's exactly what this room is for, actually. So let's make a new type called animal. It's a type union of send bird, send bat, send cow, send sheep, send rabbit. Let's make a new thing of type animal with the face A and the value send cow. And then let's feed it to this switch statement. So I'm going to type all this in the dojo. And notice that this code down here, we're only covering the cases send bird and send bat. And for every other case, we're just saying use this default behavior right here. Don't do any of these. Use the default behavior if you don't get any matches. So what happens is cow cannot fly, right? And we can do the same thing, except change the value for A to be bird, and then have our switch statement again. And then in that case, it picked it up here, did this branch, and returned I can fly. All right. So are there any questions on that? Okay, so it looks like I have about 5 or 6 minutes remaining. So what I'm going to do is have a short introduction to what we're going to learn. What's the order of evaluation? Sorry, I don't completely parse that question. Maybe you could rephrase it. For the pattern match, I'm pretty sure it just goes in order that they're written. I think for the what less, it just goes down these in order, and if it doesn't hit any of those, then it goes back to the default one. All right, yeah. So I'm pretty sure the way, so it's written first, but I think like this is it does this last. So I'm pretty sure it's the same as other languages. I'm not 100% on that, but yeah. All right, yeah. Any other questions on this pattern matching? All right. So our next topic is going to be lists. So if you recall, if I make a cell type of 2 numbers like this, right? So I define this new cell type called 2nums, and it's a PAUD in the first place and a PAUD in the second place, right? And that won't fit a cell of 3 numbers, right? If we try to ket-hep that, that's going to fail. And likewise, a type that's a cell of 3 numbers is not going to fit a cell of value that's a cell of 2 numbers, right? So that's going to fail as well, but we're fine about that. So we get a failure. So that doesn't fit that. However, sometimes you need a data type that doesn't know in advance how many entries it's going to have, right? Like it can be, we say like we need numbers in this data type, but it's going to have like 5 entries or 10 entries, or it can keep changing, right? We don't know. And that role is fulfilled by lists in Hoon. So a list is a structure with the same data type in every entry and a variable length to it. So let's try a simple example of making a list of numbers. We use the syntax like this. And let's try to dissect what's going on here. So recalling that everything in Urbit is a binary tree. When we have this command, this 1, 2, 3, 4, 5 sig, the internal data representation should look like this, right? And if we want to represent this in a cell format, it'll look like this, right? So you have a cell of 5 and sig, which is inside a cell of 4 and 5 sig, which is inside a cell of 3 and 4, 5 sig, and so on, right? This sugars to this. And there's also another sugar syntax that we are going to just learn now, which is you pull this sig out and you put it in front. And the reason you do this is because the sig, this is what differentiates this from just the cell of cells. The sig in the last position helps you know that it's a list. And so putting it in front just helps readability, but this is just sugar syntax for this. So I can just type this here and these are equivalent. So let's try to parse this expression a little more. So what's going on here? We should notice this senhep room again, right? What does this mean? This means we're calling a gate, right? And in fact, this term list is actually, yeah, so the question is, what's the difference between 1, 2 sig and 1, 2? So 1, 2, well, they're different things, right? If you look at them just as cells, the cell 1, 2 is literally just the cell 1, 2, whereas 1, 2 sig that's a cell of 1 and 2 and sig, right? So on the cell level, they're different things, but this can't be interpreted as a list, whereas this can be interpreted as a list because it has a sig in the last position. All right, looks like I'm running out of time, so I will save lists for the next lesson, but we should have the mystery of the senhep list PAT-UD. This mystery right here should be on our minds. But all right. So yeah, I will release the homework hopefully within 24 hours. But any final questions on any part of the lesson or any concerns? Yes, 1, 2 is a binary cell, is not a list. Any list must have the sig at the end. I have anonymous feedback here. Feel free to say whatever you like in there. So yeah. All right, so if there's no more questions, I will end this recording. Yep. Thank you guys for being here. And as a reminder, I'll have office hours in 15 minutes. Yeah, thank you, folks. Have a great weekend as well. All right.